Okay, this video is to show you how to work the third level of the DC single node pair single loop tutorial, and in particular how to use some of the new features at this level, which include the interactive circuit editor, which may be one of the more complicated things to understand. So as usual, you will have to do the corresponding section of the tutorial before you can access this. It's always great to look at some examples. In this case, there's going to be multiple screens here because there's several steps to some of these tutorials where we're actually simplifying things, and so you can scroll down to see those different steps. Okay, so let's start with the first problem type. And in this case, the idea of this problem is actually to use voltage division. That's a big theme in this entire game, because for single loop circuits that's what you try to do. But unfortunately we can't do that because there's two different voltage sources. And in fact, there's actually a special thing that happens in this case, which is a little unusual, which is that those voltage sources are going to annihilate each other because they have opposite polarity. So actually, to get a little bit more typical example, I'm going to generate a different problem there so that I can show you all the features. So that won't happen here. Okay, so we're going to simplify the circuit, and that means to use the interactive circuit editor. So we're going to click on that button. And now it puts us in the circuit editing mode. And this is called the pre-simplification mode. The circuit editor actually has several different modes that you will use in different exercises. So what we're going to try to do here is to combine things in series. And the most important thing is actually to combine these voltage sources, because without doing that, we can't use the simple voltage divider formulas that would be the best thing to use. So in order to do that, we're going to combine these two sources, and so we have to look at the polarity here and say, okay, this is a 5-volt rise followed by a 6-volt rise as I go around in a clockwise direction. So the net rise there is actually 11 volts. So I'm going to click on that and enter 11. And then this source now, to turn that off, basically, I have to change it to a short circuit. So there's several ways to do that. I can right-click on it and select element type and then go to short. That would be one way to do it. I could also just click over here on this little short icon with that element selected. When it's selected, you'll note that it's turned red. So that will turn it red. Now, the principle of the circuit editor is that you can only do one type of simplification at a time, and you have to tell it when you're done so that it can give you the step-based feedback that is the core idea in this program. So if you start doing something else now, like combining these resistors, it's going to tell you, no, don't do that. So I'll show you, for example, if I were to change that value, it's going to say that's not a part of the series set that you're currently combining, so you should leave it alone, and it's not going to count that against you as an error, but it's going to tell you finish what you started, basically. So I need to check the combination with this button over here anytime I combine some circuit elements. And now it tells me I did it correctly. If I did it incorrectly, of course, then it would count the error, and you'd have only a certain number of errors that you're allowed to make. Now, it might also help, in fact, it will help here to combine these resistors, because our program actually can't accommodate more than 3 resistors in a voltage division term just because of the way it's set up. So I will want to combine these. And so the thing is here, I cannot combine the 2 ohm with the others, this 2 ohm, that is. And the reason is that it has a sought voltage. So as discussed in the tutorial, if I were to combine this, either I would change the voltage across this resistor, or that resistor just wouldn't be there anymore and I wouldn't be able to have that sought voltage. So either way, it's going to change the answer, and therefore it's not a legal operation. So I need to leave this one alone because it does have a sought voltage. A sought current wouldn't matter because the current would flow regardless of combining it, but the sought voltage does matter there. So I'm just going to combine these other 3, and that's 7 plus 7 plus 2 is 16. So I'm going to make this a 16, and then again, since I'm basically combining that, I need to make it into a short. So I would do that here, or as I said, I could do it this way. And once again, I have to check the combination when I'm done. Now, if I forgot what I was doing or I got mixed up or something, I can always click the Restore Circuit button, and that will bring back the circuit in the last state where it was valid, after the voltage sources were combined. I'm not going to do that here, but you always have that option. So I'm going to check that combination, and it tells me it is correct. And now I've basically done all that I can do here, and so I tell it that I'm done editing. Now what you don't want to do is typically click the close box here without clicking that button, because that will simply abort all your changes. If I try to do that, it'll warn me that I'm going to abort, and that's not what I want to do. So I'm going to click Done Editing, and then it'll be done. And notice there also was a help button in there which you could have clicked, and there will also be a video help button after I finish recording this video. Okay, so now we notice we do have a single loop circuit, so we will select single loop analysis. It's not a single node pair because there's actually 3 nodes there. And then I need that sought voltage, and now because it's in a form where I can use voltage division, namely it has only one independent voltage source, I can go straight to writing the voltage division formula here. And again, I apologize for this artifact here of my screen capture program. But okay, so the V0 equals, in this case, I'm going to use the standard term here. So I have an 11 volt source, and then the resistor of interest is 2 ohms. That's going to go in the numerator, and then the denominator will be the sum of the 2 plus the 16. And here I am allowed to combine those because I did it in the circuit editor. So notice that before I wasn't allowed to combine resistors if I do it outside the circuit editor, but in the circuit editor, then it's okay if you combine them and use a single term. Now I do have to check, and remember that the 11 volts here divided by the 18 ohms, that's going to be the current that's actually circulating in this direction. Okay. Now I have to check as to whether I need a plus or minus sign, as always. So the positive side of the 11 volt is actually connected to the positive side of my sought voltage, and the negative goes to the negative, so that's the same polarity, the same sense. Therefore, I do need a plus sign here, and that will be correct. So I click that button, that's correct, and then that's all the equations I need here. So now I just need to numerically evaluate that with my calculator. That's 2 over 18 times 11, so it'd be 22 over 18, so that'd be 1.22, and that's finishes that problem. And again, you can always get a detailed solution. In this case, it's going to just take the simplifications that you already did and base it on that rather than showing you the actual simplification. If you showed a solution at the beginning of the problem, it would actually show you how you simplify it as well. Okay, now let's do the second problem type. And again, most of these are going to involve the circuit editor, or at least can involve the circuit editor. And now this time I actually have a single node pair circuit, if you'll notice, because here's one node here and then another node here. And again, because this could be a current division problem, if I simply combined these current sources, notice that they're all in parallel, which is obvious because I only have 2 nodes. They have to be in parallel. Therefore, to use the standard current division formula, I must combine these current sources. And so that's where I need to go into the circuit editor to do that, because the problem wants you basically to use the current division formula. It's not absolutely required, but it's really quite a bit easier, I think, to do that. Okay, so in this case, I'll notice that the 2 amp is opposite to the 3 amp, and then because the 2 amp is going out of this node, the 3 amp is going in, and the 1 amp is going in. So I have 4 in, 2 out. So that's basically the equivalent to a net, let's see, 4 in and 2 out would be equivalent to 2 in. So I'm going to make this a 2. And then this one, now instead of changing it to a short circuit, I need to turn it off, which means in this case I have to change it to an open circuit. So I can just hit the delete key on the keyboard, or I can use this delete button here, or I can right click it and select delete from that menu. So there's 3 different ways to do that. And then this one I also need to delete, so this time I'll just use the keyboard. And so now I've deleted those, and again I have to check what I'm doing, so I'm going to check that combination. Now you might say, well, these resistors are in parallel, you could combine them, and in theory you could, but the problem is that you would then not have this current I0 anymore, which is the sought current. So that we're going to leave alone, and we're actually going to quit the circuit editor at this point by saying that we're done editing. And I will just show you this help feature, by the way, while we're here. So this does have detailed written instructions in case you forget about how to do something. It's a little bit lengthy because there's lots of things you can do in the circuit editor, but basically it does have all the information there about what you can do, and that's a PDF file. And you could keep that open if you need it. Okay, so we're done editing. And now we have a single node pair circuit to solve. So I'm going to do single node pair analysis. It's not a single interior mesh, as you can see. And I need a sought branch current, so I would pick that type of equation. And my I0 now is going to equal what? Well, again, I have now actually 3 different choices for the current division formula. I could do it in terms of reciprocals of resistors. I can do it in terms of just resistances themselves, or in terms of conductance measured in Siemens. Remember, the Siemens, the capital S, is 1/ohm. And you can use any of those terms, or you could even use this one if you want to compute what the voltage is, or you could even use this one if you want to compute the answer separately. But I'm going to use this one. That's my favorite. So we have a 2 amp source, and now for the current divider formula, if you're doing it in terms of resistance, you have to remember that the numerator is going to be the other resistor, not the one that the current's flowing through, your I0. It's going to be the 9 ohm resistor. And then this is going to be 9 plus 5. And basically, that's explained in the tutorial. That's how the current divider formula works. Now I also have to check polarity, and I say the 2 amps is going into this node through the source, therefore it must leave through this resistor and through this resistor. And of course, current takes the path of least resistance, so you're going to have more current going this way than you do going this way. That's the basic idea of current division. So because I0 is opposite to that sense, it's going to have a minus sign here, because I0 is actually flowing into that a node there. So I need the minus sign, and that's correct, and that's all I need. So now I will simply numerically evaluate that, doing the math. 9/14 times -2 is -18/14, or -9/7, and that'll be -1.29. And again, I'm trying to enter a fraction here because that's not accepted. And now we're done. And again, I can get a detailed explanation in terms of all these different formulas, and that's actually maybe worth reviewing, so you might want to look at that. Okay, now for the third problem type, this one's going to be a little different. And you see it's a single loop circuit, but now we actually have a new type of SOT variable we haven't encountered before. This is called a non-branch voltage. Basically, it's VBA, which means this voltage minus this one. And as we can see, that doesn't actually appear across any one circuit element. It appears across 2 elements in combination. And so that's not a branch voltage. Now this one, if I simplify it, I can actually make this become a branch voltage, and I am allowed to do that in the circuit editor. I'm actually going to pick a different problem though, because I want to show you a case where you can't do that. So I'm going to pick a different problem and abort this one and generate another one that doesn't have that particular feature. So this one will be more like what I would like to show you. So again, it's VBA in this case, which is this voltage minus this one. And now we're going to try to simplify this circuit. It's not telling you have to do it, but it would be helpful, or at least somewhat helpful to do. So I'm going to go into the circuit editor. And now what I have to keep in mind, based on the information covered in the introductory tutorial, is that I cannot combine things that are on opposite sides. So imagine drawing a line from VB to VA. If I combine things that are on different sides of that line, that's going to actually change the voltage difference between VA and VB. And therefore, that would be an invalid simplification. So the SOT variables determine what you are allowed to combine in series and what you are not allowed to combine. That's a very important aspect of this. So I can combine these two sources because they're on one side of VA. And so I'm going to do that. And since these are opposite, basically the 1 volt will subtract from the 6 volts, making that 5 volts. And then I'll change this to a short. And then we have to check that step before we try to combine anything else, or it will say I can't do that. So I'm going to check that. And now, again, I cannot combine, for example, the 5 ohm and the 2 ohm, even though they're in series, because, again, they're on opposite sides of the VBA line. So, therefore, I can only combine things on the same side, which would be, for example, the 2 and the 1. And I don't have to combine them, but I think I'll just do it, just to keep my equation a little bit simpler. So, I change that to a short and check my combination, and indeed that is correct. Okay, so now I've done pretty much all I can do here, and the VA label has been relocated, but it's on the same node, so that hasn't really changed. Okay, so I'm done editing, so I'll click there. And now it is a single loop circuit, so I'm going to do single loop analysis. I could have done this without simplifying, and it wouldn't make really a lot of difference here, but I think it actually makes it a little bit easier to do it this way. So now I'm going to start out actually here by writing a KVL equation, because I need to sum those things up and determine what that current I1 is, that interior mesh current. So again, I need a separate term as always for each element that I'm writing a KVL equation for. So I have two resistors, so I'm going to need one term there. I have a voltage source, another resistor term, another voltage source, and all that has to sum to 0, as always in KVL. So first I'm going to, let's say, start here maybe, and I'm going to go through the 3 ohm resistor. So I have I1 times 3 ohms as the voltage drop traveling clockwise through that resistor. And then as I'm traveling clockwise, this is actually also a voltage drop because I'm going from plus to minus. So that'll be a +4 as opposed to a -4 if it were the other polarity. Then I go through the 5 ohm resistor, and that's, again, since I'm automatically using passive sign convention here, my I1 flows into the plus side of my drop and the minus side, if you will. That's going to be I1 times, 5. And then the last one, that's also going to be a drop because I'm going from plus to minus. But of course, either of these or both of them could have been negative. You have to just pay attention to that, which way they happen to be oriented. Okay, so that's going to be the end of that. And now I check that, and that is in fact correct. Now I also need, of course, a sought variable equation for my unknown, which is this non-branch voltage, meaning it's not across any one circuit element. It's actually across 2 elements. And you could actually compute it going 2 different ways. You can go this way, or you can go this way. And so there's actually 2 ways to write that, and it'll accept it either way as long as you do it correctly. So let's select now this one we haven't used before, this sought non-branch voltage. And now it's going to give me the terms I might need to write that equation. So of course it's going to be VAB equals, and now I basically have to use Kirchhoff's voltage law to compute that. So in other words, I have to add the voltage drops going from A to B. And so that's, one is through a resistor, if I go this way, for example, and then the other one is through a voltage source, so it would be that term. So the voltage drop going, so I want VA minus VB, so I'm going to add voltage drops going this way. So that would actually be, because it's I1 is coming into this direction, so that's going to be the active sign convention for resistor. So that's actually going to be a minus I1 times 3 ohms. And then here, again, I'm summing the voltage drops, and that's actually a rise, so that's going to be a minus 5 volts. Now, that will be correct, but I could have actually written the equation going this way too, in which case I would have had VAB is equal to 4 volts plus I1 times 5 ohms. That would be another completely different formula, but it will also be accepted by the program. So let's check the equation, and that is correct. And now I'm done. And now I need to compute my I1 from the KVL equation. That's a simple algebraic equation. I have 9, which will become minus 9 on the right side, and then I'm going to have 8 I1. So it's going to be negative 9/8, which is minus 1.12 approximately. And I'll check that. And then I need to compute the sought variable now, which is a little bit more complicated because I need to plug my I1 into here and then subtract 5 from that. So I'll do that on my calculator, and the answer will work out to be minus 1.62 volts, and that's correct. Okay, and then I can always get my detailed solution, and again, it'll be based on the pre-simplification I already did. It'll basically explain writing the KVL equation and then writing the sought variable equation. So these can be some of the trickier equations to write, so definitely take notes on the introductory tutorial so you learn how to do that systematically. Okay, and you can also get a detailed explanation of the KVL equation. Okay. Now problem type 4. This is, again, we see it's a single interior mesh type problem, not counting the outer mesh. And now we could combine some things here. Let's see what we could combine. We could actually combine this resistor and this resistor, which have no sought variables. We could also combine these voltage sources. So let's actually do all of that. So let's go in the circuit editor and simplify. And this is actually a little bit funny problem. Yeah, this is actually going to end up, the answer is going to be 0. And because I don't want this to be a trivial problem to show you, I'm going to actually generate a new problem here. I mean, we can certainly work the old problem. It would end up being simpler than what I want to show you. So, I'm going to do my, I'm going to simplify the circuit first, actually. And here again, we have voltage sources that could be combined. And, well, here we can't actually combine any resistors if you think about it, because this resistor, we need that because of its sought voltage. I'm sorry, not its sought voltage, it's control voltage that controls this voltage controlled voltage source. And so if we were to combine that resistor, that voltage would be gone, so we have to keep it. And likewise, we can't combine this resistor because it has a sought voltage across it. So if there's a voltage across a resistor, we cannot combine them in series because we would lose those critical voltages that we need. And this one, of course, is only one, so we can't combine it. What we could do in the circuit editor is to combine these two sources. And it's not critical that you do that, but let's go ahead and do it anyway, just for fun. And so these are kind of opposite polarity. They're minus to minus. So that means that this is basically going to negate part of this. And so we're going to have 7 minus 3, or 4. And then we'll change this to a short and check that one combination. And that's basically all that we can do. If I were to try to, for example, change this value, it's going to tell me, oh, I can't do that because that's going to change the control variable value. And so that's not allowed. So I have to be done here, basically. And now I'm going to write equations. So I have to select the analysis, which in this case, there's one loop, interior loop at least. So I'll select that. And now I'm going to need a KVL equation because it is a single loop problem. And it's not clearly a current divider, or I'm sorry, not a voltage divider, I mean, because you cannot combine an independent with a dependent source because those just are not combinable. So unfortunately, we cannot use the simple voltage division formula here. And anytime you have a dependent source, that's generally going to be the case. You can't use simple voltage or current division. So here I'm going to write a conventional KVL equation. And so I'm going to need a term for each element, separate term. So I'm going to need, I have 3 resistors, so I have a resistor there. I'm actually going to need a term for this. So that's the voltage controlled voltage source. So that's going to take this form. And you can actually hover over that and it'll tell you that that's what that's for. And then 2 resistors here, so 2 more resistor terms, and then a independent voltage source, which has a fixed value, and that's all going to equal 0. Okay. So now, again, I'm going to add voltage drops going clockwise in the direction of I1. So here we have I1 times, say, 6 ohms. And then now I'm encountering a negative sign first. That means this is actually a voltage rise by an amount 3Vx. And since I'm adding drops, that becomes a minus. And so that'll be minus 3. And then the subscript here should be X for Vx. And then the next resistor, the 1 ohm resistor, is just going to be I1 times 1. And then the next one would be I1 times 9. And then finally, we're encountering now down here the plus side of the 4 volt source. That means this is actually a drop, so it will have a plus sign of 4 volts. And that would be the equation. And now notice that I actually need 2 additional equations, and that's because I have a dependent source. So one of the things we haven't done before is to have an equation for a control variable of a dependent source. In other words, this Vx value that controls this source. So we need to write a separate equation for that, otherwise we won't have enough equations. The problem is, we have 2 unknowns in this equation, both I1 and Vx. And if we don't have another way of relating that, of course, we can't solve for either one of them. We need 2 equations and 2 unknowns. So we need to write a new type of equation, which is called a control variable equation. And you need this anytime you have a dependent source of any kind. So those little diamond-shaped sources are dependent sources. So I'll click that, and the control variable in here is going to be Vx. So I'm going to use this term and fill in the X. And that should equal to what? Well, this term wouldn't even have the right units, right? That would be units of amps, and this is a voltage. So that can't possibly be the right term. So I need this term, which is going to have units of volts. And basically, it's Ohm's law. So it's Ohm's law, however, with active sign convention, because I1 is entering the negative sign of the Vx voltage. That's active sign convention. So I have a minus sign in my Ohm's law equation, and that's going to be I1 times 9 ohms. Again, if I got the sign wrong, it would reject the equation. Okay, and then finally I need my sought variable, which in this case is my V0. And so that's a sought branch voltage, so I select that type because that's across one element, as opposed to the previous problem, it was across more than one element. Now, I can't use a voltage divider formula here. It's being offered to me, but that would be incorrect because there's just no way to use that when you have a dependent source. So my V0 here, I have to use Ohm's law. And of course the current's going to be I1, that's the only current in this circuit. and we know it's going to be the 1 ohm because that's the resistor involved for V0. But the only question then is the polarity, and here it's actually passive sign convention because I1 goes into the positive terminal V0, therefore V equals IR, not V equals minus IR. So that'll be the correct version. And now I'm done because I've done everything that's required here. And now I need to solve I1, but I actually have to combine this equation with this one, which I probably want to do that on a piece of paper. I mean, you can imagine plugging that in here. It's going to basically make 27 I1 here. And then you add up all the I1 terms, bring the constant over, of course, and just solve using simple algebra. And when we do that, we're going to get negative 0.093 amperes. After you solve that, probably on paper would be a good idea. And we'll check that. And then the next step, of course, is to find the variable we wanted, which was V0. And so we're going to have to use this equation. So in this case, we just multiply I1 times 1 ohm. That's obviously very easy because it's multiplying by 1. So that'll be just minus 0.093. So there's the value of I1. It also shows you the value of Vx, which it didn't actually force you to compute, but it's there for reference anyway. Okay, so that's done. And we have finished that problem. And once again, we can get a complete explanation, including the illustration of the voltage drops here. And in addition, there's a couple of new things here. It'll actually explain to you a little bit more in detail if you've forgotten what a dependent source is. It has help explaining that, although it explains it probably in terms of more complicated circuits, but it does explain it. And it'll also explain what a control variable equation is and how you write that. So if you find that confusing, then you can get an explanation of that here. Okay, and then you can also get an explanation of the color-coded KVL equation if you need that. Okay, so that finishes that problem, and we have one more level. One more, or not level, but one more problem. And this one also has a dependent source, as you can see here. This is actually a current-dependent or current-controlled current source. And you see that this is actually a single node pair circuit. So let's think, could we simplify this at all? And in this case, there's actually no simplification possible because if we combined these three resistors in parallel, well, we'd be losing I0 and we'd also be losing IX. And that would just be no good at all because then we couldn't solve the problem. And likewise, we can't combine these current sources because one is dependent and the other is independent, and those can never be combined. So there's actually no useful simplification that can be done here. So there's really no point here in going into the circuit editor. So instead, I'm just going to solve this as a single node pair circuit, and it's color coding me the nodes for me now, and it's put a reference node on there. So now I need a SOT branch current, and here it's telling me there's actually two palettes of terms, as there sometimes is for power. Here there's also for this. So the SOT branch current here, well, you might think I could use a current divider formula, but that actually won't work here because you have a dependent source. Those never work when there's dependent sources. So don't try to use those terms. They won't work. Instead, I'll have to go to the second set of terms here. And I can see that my I0 would actually be expressible in terms of V1 and that resistor using Ohm's law. So I'm going to use that. And so it's V1 divided by that 1 ohm. But I have to be careful because the voltage that causes that current to flow is actually 0 minus V1. So that means there's going to be a negative sign. In other words, this is the active sign convention. So I need a minus sign there. Or I could also put the minus sign over here if I want and make this a plus sign. There's freedom there. Or as I said, you could have them, well, I guess it doesn't give you a zero term to use. But anyway, you could do that in different ways. Okay, so that's my SOT variable equation. But I also need a KCL equation. And so I will select KCL equation. It's giving me that big hint there that that's what I need. And of course that's so that I can determine the value of V1, because after all this is expressed in terms of V1, so clearly I have to have an equation that I can solve for V1, and that would be a KCL equation when you're dealing with a single node pair circuit. So I'm going to have, let's see, a current through a resistor, current through a current source here, a current controlled current source, which would be this type of term here, another two resistor terms, which would look like this, and then that's all equal to 0. Okay, so I'm going to add the currents leaving the red node, the V1, so that would be V1 over 1, And again, I use the tab key to make this easier. And since this current is actually flowing into V1, that's going to be a minus 2 amps, not a plus. And then likewise, this current is flowing in rather than out, so that's also going to be a minus sign, but now it's minus 6 times Ix. So I have to put the X there and place the alpha. Remember, the alpha stands for letters, and that's what you're supposed to fill in. The N is a number, but it's an integer. This is a number that isn't always an integer, although in this case it will be. So now we have V1 over 5 for the current leaving through the 5 ohm resistor, and then V1 over 2 for the current leaving the top node through that resistor. And those all have to sum to 0 by virtue of KCL, Kirchhoff's current law. So I'll check that equation, and that is correct. But notice I still have one more to write, which is the control variable, because anytime I have a dependent source, I have to write a control variable equation. In other words, I have this Ix, but I don't have enough equations. I have really 3 unknowns, V1, Ix, and I naught, if you will, and only 2 equations. That's not enough. So I have to have a control variable equation. So you use those control variable equations, again, when you have dependent sources. So in this case, it's an Ix that I'm trying to find, so I'll use that term. And I have to fill that alpha in as being X there. And I'll use Ohm's law to get that, so that would be this term. And again, the other terms wouldn't even have the right units, so you certainly wouldn't use those. And that's going to be V1 divided by 5 ohms, because volts over ohms is an amp, which is what I need for my current. Now I also have to check the polarity, as always, and this is actually, the current that drives this is actually going to be 0 minus V1. In other words, that's an active sign convention situation, and so that has to be a minus sign. Okay, so now I've got all my equations. I click no more equations, as always, and then I just solve these 2 equations together for V1. I'd have to substitute this one, of course, into this, which I'd probably want to do on paper, but you can see it would be kind of plus 1.2 V1, and then you combine it with all the others after putting everything in decimal form. Or you could clear the fractions and do it that way if you like. But in any case, with my calculator and some algebra, I would find that that's 0.69 volts. Check that, and that's correct. And then I've got to use my slot variable equation. So that's this equation here. And so basically that's just going to be the negative of V1. And so it would be minus 0.69 volts, since V1, as it already showed me there, is 0.69. Okay. And once again, we can get a detailed explanation with the color coding showing you each of those currents adding up, and it explains the control current and the SOT current. And there's also, again, these detailed explanations you can get here if you need that. Okay, so that completes that level. Thank you.